Welcome to the lesson on Euclid's division lemma. At the end of this lesson, you will be able to state the principle of Euclid's division lemma and calculate the highest common factor of any two positive integers by applying Euclid's division lemma. You will also be able to identify certain properties of numbers by applying Euclid's division lemma. Meet Mr. Chatura. He runs a stationery shop. To keep a track of all the items in his shop, he uses a special form. Right now, he's checking his stock. Let's take a closer look at his form. The first column of this table shows the names of different items Mr. Chatura sells. The second column shows the number of items in standard boxes available. Now, let's follow Mr. Chatura as he fills his table. Each box of pencils has 12 pencils, and Mr. Chatura has 5 such boxes. This means that there are 60 pencils in the boxes. He also has 3 extra pencils. Thus, the total number of pencils is 63. Each box of erasers has 10 erasers, and Mr. Chatura has 8 such boxes. This means that there are 80 erasers in the boxes. He also has 6 extra erasers. Thus, the total number of erasers he has is 86. Each box of sharpeners has 8 sharpeners, and Mr. Chatura has 4 such boxes. This means that there are 32 sharpeners in the boxes. He does not have any additional sharpeners. Thus, the total number of sharpeners is 32. Each box of ballpoint pens has 15 pens. But right now, Mr. Chatura doesn't have a complete box. He has 10 extra ballpoint pens. Thus, the total number of ballpoint pens he has is 10. Now pay attention to the values in each row of the table. In the first row, the total 63 is equal to 12 multiplied by 5 plus 3. Similarly, in the second row, 86 is equal to 10 multiplied by 8 plus 6. The last two rows are interesting. In the third row, we can say 32 is equal to 8 multiplied by 4 plus 0. Similarly, in the fourth row, 10 is equal to 15 multiplied by 0 plus 10. Now, let us come to the point. If we assign labels to the values in the different columns of the table, we can see that they all follow a general relation. The total A is equal to the pieces per box, B, multiplied by the number of boxes, Q, plus additional items, R. This relation is known as Euclid's division lemma, which states that for any two positive integers, A and B, we can find two whole numbers, Q and R, such that A is equal to B multiplied by Q plus R. From Mr. Chatura's table, you can see that Euclid's division lemma holds true even if either Q or R is 0. Now suppose Mr. Chatura discovers he has 12 extra pencils instead of 3. What happens to Euclid's division lemma in this case? 12 pencils add up to one complete box. So we see that if R becomes equal to B, the value of Q increases by 1 and the value of R is reduced to 0. Thus, the value of R in the equation for Euclid's division lemma can be greater than or equal to 0 and less than the value of B. Mr. Chatura has got a fresh stock of pencils and erasers. He is making space to arrange them on the shelves. Mr. Chatura has got 520 boxes of pencils and 140 boxes of erasers. He wants to arrange them in the least number of shelves, such that each shelf has an equal number of boxes of pencils and an equal number of boxes of erasers. Mr. Chatura has figured out a solution. All he has to do is find the highest common factor, or HCF, of 520 and 140. Now, how does he do that? Mr. Chatura can use Euclid's division lemma to find the HCF of 520 and 140. Let's see how. Let's apply Euclid's division lemma to the two numbers taking the larger number equal to A and the smaller number equal to B. Dividing 520 by 140, we see that 140 goes into 520 3 times and leaves a remainder of 100. Now consider the value of B and R in this equation. We see that R is not 0. So let's apply Euclid's division lemma, taking 140 as A and 100 as B. Dividing 140 by 100, we see that 100 goes into 140 once and leaves a remainder of 40. Now consider the values of b and r in this equation. We see that r is not 0. So let's apply Euclid's division lemma, taking 100 as a and 40 as b. Dividing 100 by 40, we see that 40 goes into 100 two times and leaves a remainder of 20. Now consider the values of b and r in this equation. We see that r is still not 0. So let's apply Euclid's division lemma, taking 40 as a and 20 as b. Dividing 40 by 20, we see that the 20 goes into 42 times and leaves a remainder of 0. Note that in this equation, the value of r has become 0. The value of b in this case, that is 20, which is the HCF of the numbers 520 and 140. By Euclid's division lemma, we found that HCF of 520 and 140 is 20. Thus, Mr. Chatura can arrange his stock in 20 shelves, each having 26 boxes of pencils and 7 boxes of erasers. Now, let's observe the process of finding the HCF of any two given positive integers using Euclid's division lemma. Suppose we have two positive integers, a and b, such that a is greater than b. Apply Euclid's division lemma to the given integers a and b to find two whole numbers q and r, such that a is equal to b multiplied by q plus r. Check the value of r if r is equal to 0. Then, b is the HCF of the given numbers. If r is not equal to 0, apply Euclid's division lemma to the new divisor b and the remainder r. Continue this process till the remainder r becomes 0. The value of the divisor b in that case is the HCF of the two given numbers. Euclid's division algorithm can also be used to find some common properties of numbers. Let's take this problem to show that every positive odd integer is of the form 2q plus 1. Let a be any positive odd integer. Then, by Euclid's division lemma, we can write a is equal to b multiplied by q plus r. If we take the value of b as 2, we can write a is equal to 2 multiplied by q plus r. By Euclid's division lemma, the value of r can be greater than or equal to 0 and less than b. Since b is equal to 2, the possible values of r are 0 and 1. Putting in the values of r as either 0 or 1, we get the possible values of a as either 2q or 2q plus 1. Now the value of a cannot be 2q, since 2q is divisible by 2 and a is an odd integer. Thus we can say that any positive odd integer can be of the form 2q plus 1. You've reached the end of this section. Let's have a quick recap of the key points covered in this section. Recall that Euclid's division lemma states that for any two positive integers a and b, we can find two whole numbers q and r, such that a is equal to bq plus r, where r is greater than or equal to 0 and less than b. Euclid's division lemma can be used to find the highest common factor of any two positive integers. It can also be used to show the common properties of numbers. You can now proceed to the next section. Hope you enjoyed this learning experience.